This lecture is going to look at some of the data hiding and obfuscation techniques that someone might do to maliciously hide information. So we'll look at the main obfuscation methods, define some of the methods that are used to encode data to hide the original content, understand encryption methods used to hide data, and the methods that we could use to overcome this obfuscation, and also we'll define some of the file types that could be discovered by a deep scan of a file system. So let's look at one method which is fairly difficult to actually determine the original information, and that's where a malicious person might use obfuscation by encryption. The four main methods that we can have related to this include the encryption methods, and also it's possible to hide information through various types of encoding. So with private key encryption or symmetric encryption, we have one key which will encrypt, and then the same key can then decrypt it. So typical methods we use here are RC2, RC4, DES, 3DES and AES. With asymmetric encryption we have two keys, one to encrypt and another to decrypt. So in this case we can encrypt with one key, such as the public key, and then we use a special key to then decrypt the message. So typical methods here are RSA, DSA and so on. We can also get an encryption process which is one way, and we typically define that as a one-way hash. With this method it should be computationally difficult to reverse the hash back into the original message. So typical methods that we have for hashing are MD5 and SHA1. For encoding, information could be hidden through the usage of hex, base 64, ASCII, UTF-16 and so on. So the three main methods that we can use if there is malicious information which has been encrypted is to do a search for key strings on a file system. So this will typically bring up key phrases that might have been used within the password. If these fail when we try to decrypt the ciphertext, then a dictionary could be used, of which we have a standard dictionary here. And then if the dictionary fails, then it's possible to go for brute force. A typical method here is to use a processor farm where we have multiple processors, each will be given a range of keys, and then we'll iterate through those keys until a success is found. With encryption, if we look at the encryption process here, so we will have a look at some private key encryption. So with encryption we might have a message, and when we encrypt it we get our hex and our base 64. Again, we can use AES. So let's look at the principles of brute force encryption. So what we'll do is we'll take some text, we'll put it through an encryption process for AES, and we get an encrypted hex. What should happen is that the program will go through and try a range of names from a standard dictionary. An exception is caused when the wrong key is actually used. So what we'll do is we'll try to see if we can actually decrypt it. So we can see one is possible there, and we can actually stop it now. So you can see here, for all the words that it's tried, it's created an exception for most of them, and only 3 have appeared here. We can see that achieved obviously isn't the original text. Appears doesn't seem to work either, and you can see we've actually found the keyword, which is apples in this case, and it's decrypted the content with the word test. Okay, so the principle is that we have encryption, we have our ciphertext, and then through a dictionary it's possible to search through standard terms to be able to find the malicious content. Okay, so this is an example of 3DES and AES. And then what we did was that we took some plain text, used an encryption key to get our ciphertext. We then went through a range of words, and we can see here it picked off the encryption key. The other method that might be used is public key encryption, and public key encryption basically works like this. Bob wants to send to Alice. Alice sends her public key to Bob, normally in the terms of a digital certificate, whereas that only contains the public key and not the private key. Bob then encrypts the message. It goes to Alice. Alice then uses her private key to be able to decrypt the ciphertext. It's also possible for Bob to sign the message. He takes a hash of the message, signs it with his private key, forwards his public key to confirm his identity. Alice then decrypts the encrypted hash, and if it's the same as the hash for the message, then she has verified that it was Bob that sent the message. It's obviously more difficult with public key encryption to actually determine the original key, and we end up with two types of certificate. One certificate, as we have here, has the private key stored in it and also has the public key. The certificate which is distributed only contains the public key. So one method, if we have some malicious ciphertext which uses public and private key, one method to be able to decrypt the message is to try and find out the place where the public and private keys are actually stored. So this might involve a brute force attack on the digital certificate, which is typically protected by a password. So once the password is broken, then it might be possible to get the private key from it. Another method that a malicious party might use to hide information is to obfuscate it by hashing. So hashing works by taking any size of message and then converting it into a standard hash signature. So in this case, base64 has 128 bits signature. Each one of these characters represents 6 bits. Each one of these characters represents 4 bits. So we take the original plaintext, feed it through our MD5 algorithm, and we get a standard hash signature or fingerprint for each message. With SHA1 we get a longer signature. The longer the signature they get, the less likely that another signature, the same signature, can occur for a different message. So in this case we have longer signature for both the base64 and hex. To calculate the number of characters, it's roughly 160 divided by 6 in this case, and 160 divided by 4 in this case. So what we get is that all we need to do is change one character or one bit of information, and it completely changes the hash signature of the converted hash message. So we'll try here. So for a standard hash signature, so we can take some examples here. This is MD5, this is base64 for test. So we can do test 1, 2, 3, 4 and so on. So we can see that every time we change it, then we get a new hash signature. So let's try our hash signature for apples. So we'll just copy that and we'll paste it into here, and we'll do a search through a standard alphabet, and it should start searching, and what we get is a hash MD5 collision. Just takes a little minute to get there, and we can see here that it's actually found one. So it's calculated the hash signature for apples has to be this, which is the same as the hash signature that we have. So to overcome this, we can add salt to make sure that, from our point of view, that it becomes more difficult to find the original message. Another method that a malicious party might use to hide messages is to obfuscate by encoding the message. So two standard ways that standard text, standard ASCII characters can be converted into an encoded format is into hexadecimal and also in base64. These formats make it fairly easy to interpret binary information and also to send that information in a text format. So in this case we could have an encryption process, and then we have a bit stream, and it's fairly easy for the system to convert that into hex or base64. So the way that hexadecimal works is that we split the binary stream into groups of 4 bits, and then it's fairly easy to convert each of these 4 bits into a hex character. So in this case we have 7, and the second one we have 4, and so on. So if we have a look at our toolkit, and what we're looking for is coding. Okay, so we can see that we can enter our ASCII value, and then it should give us a hexadecimal for the equivalent binary stream. So we can see here in this case this is a 6, we have another 6, and so on. So Freddy is defined in binary as this if we use ASCII encoding, and as hexadecimal we get this as a resultant. The other format that can be used, that might be used, is with base64. With base64 we want to be able to transmit a binary stream, and it might be a Word document or some other binary document, and we want to be able to transmit in a standard ASCII format. So we split the bits into 6, and then we determine the character which is associated with it. So in this case it's a 1, so we have a 2, 4, 8 and a 16. So we should find that that is a 26, and so the character in this case is an A. So we'll do the same again. So it's AVGS B G8. Okay, so we can see the original message was actually hello. So in the toolkit we can either enter a an ASCII string. We can also enter our base 64, so we'll just do that again. This time we'll paste it in. Or we can take a hexadecimal value, and we can see again it converts it, and it will give us the binary bit stream. Another method that might be used is to use the exclusive OR operator. With exclusive OR, we don't actually lose any information when we exclusive OR a bit stream. This is a typical method used in web encryption. So with exclusive OR, a 0 and a 0 gives us a 0, and a 0 and a 1 gives us a 1, a 1 and a 0 gives us 1, and a 1 and a 1 gives us 0. So we can see here we have an original message, which is hello, and we're going to use an exclusive OR key of a small lowercase a. So this is a here, this is the bit stream, and then we encode by exclusive ORing our bit stream with our key, and we get the result here. So a 0 and a 0 gives us 0, a 1 and a 1 gives us 0, and so on. So here's an example: 0 and a 1 gives us 1, and so on. So the result of this gives us 09, 04, 0D, 0D, 0E in hexadecimal, which gives us this here. And we get an equivalent in base 64. So let's take that as an example. Go back to our toolkit, and here we are. And we'll go for hello. We'll take an exclusive OR key of A. So this is the hex stream and the base 64. And we can see here what's happened is that it's converted it into non-printing characters. So 09 isn't a printable character, 04 isn't either, and so on. So then we'll copy that over, and we can see here if we use a key of A, then we get the result back again. So you can see exclusive OR is one method, and it's a typical operator which is used in many encryption processes. One way that we can analyze a stream to find out if there is any hidden information is to look at the probabilities of the letters involved. So in this case we take some standard text, and then if we do a league table of the actual occurrences, then we find that there's 170 occurrences of E, 120 of T, and so on. So from standard English, this is our typical probability list. E is the most probable, followed by T, and then O, right the way down to Z. So for this, we can actually take our text and we can actually put them against what's most probable, and we can see here it gets it right on many occasions. Even if it doesn't get it right, then it is only out by 1 or 2 places. So the E is correct, the T is correct, the O should have been there, I there, N is correct, the A is only 2 spaces off, and so on. So let's have a look at our toolkit. We'll try some sample English text. So we can see here in this piece of text there are 175 E's, 146 T's, and so on. So when we put it against the standard text, we can see the E is correct, the T is correct, the N is slightly out there, the O is correct, the A is correct, the O is correct, and so on. So we can see here we can analyze text to be able to find the basic probabilities of the letters. If someone has scrambled the letters, then it's possible to actually analyze the cipher stream for its probabilities so that the code can be determined. So in this case we can see here that O is the most probable letter with 145 occurrences, and that is likely to equate to an E. So let's try that in our toolkit. find this scrambled. Okay, so this is we've taken some text and then we've scrambled it, and now what we'll do is we'll take it back into a frequency analysis. And in this case, I is the most probable, followed by B, and so on. So you can see there when we scrambled it, an E is actually an I, so we got that correct. So we could substitute that back in. B looks to be the second most popular, so the B is a T, and again it's got that correct. So B is actually a T, and so on. So you can see that by analysing the frequencies, there are certain probabilities in there to be able to decode the message. An extremely difficult method to be able to detect any maliciousness is where some data is obfuscated through tunneling. So with tunneling, what we can get is we can get end-to-end tunnels. In this case, Bob and Alice have set up their systems so that the complete path from Bob to Alice is encrypted, so none of the devices along the way can actually interpret the contents of what's inside the tunnel. What is more common is that we get encryption or a tunnel over a public channel. If this happens, then the actual content is unencrypted after the tunnel. So if we want to stop end-to-end tunnels from happening, then we can identify UDP port 500, as this is used for the key exchange between Bob and Alice. So this could be blocked by the firewall. We can also detect TCP protocol 50 for the actual transmission of the encrypted data packets, and protocol 51 for the authentication header within IPsec. So this shows an example conversation, and we can see here port 500 UDP is used. So this is the client communicating with the VPN server, the VPN server replying back, and then so on. So there is a negotiation of the keys here. Another method, so VPN and IPsec are fairly complex protocols. More recently, we now have the tunneling of application layer protocols through SSL. It is much less secure, but from a performance point of view, it is much improved. So with this, the secure sockets sit in between the transport layer and the application layer and try to encrypt all the content so that it is tunneled through the internet back to the other device. Standard ports have been used for application layer protocols, such as 443 for HTTP tunneled, 465 for SMTP email tunneled, 995 for POP tunneled, and so on. And with this, what we get is that the server is set up with a digital certificate. When the user connects initially through SSL to the server, then a digital certificate is passed to the user. The user should check it. Once it's checked, then it normally resides in their digital store, the certificate store, so that there is no need to check the certificate again. Unfortunately, it can suffer from man-in-the-middle attack, where the man-in-the-middle could actually pass the certificate, a fake certificate, back to the user. So we can see here an example of HTTPS. So the connection here is made to the secure socket connection for HTTP. Then the server replies back, with a synac, and then we get an ACK to say that the client accepts this, and then we can see we get a tunneling of the information. Another problem that we're facing is that the internet's been created through standard ports, TCP ports, 21 for FTP, 23 Telnet, 25 SMTP, 110 for POP. And firewalls were typically set up to be able to detect the usage of these ports, especially for the incoming SYN connection. Increasingly though, it is well known that port 80 is often allowed through a firewall, so increasingly protocols such as FTP, email and so on are actually tunneled through the firewall on port 80 or protocol or ports which are open. So let's have a look at covert channels, which could be one method that a malicious person could pass information through a standard communications channel. A covert channel is often used when there are two suspects and each suspect know they're being viewed, so we'll typically try to send, or could try to send, information which is hidden from the normal communications. So we can actually have a storage channel, and that's where a process writes directly to a stored resource, and the other suspect might read this. We can also have a timing channel, covert channel. In this case, the suspect could start a process, and that would be detected as a 1. Start the process at another given time, again that could be a 1, and then stop the process, and that could be interpreted as a 0. So in this way a message could be passed between the two suspects without the monitoring parties knowing that the message has been sent. Within IP and TCP there are places inside the protocol which allow for data to be passed covertly. This could be within the TTL field. The TTL field is there to make sure that a data packet never transverses the internet forever. So every router that it sees will decrement the TTL field by a certain amount. Once it gets to 0, then it will be discarded. The fragment offset is sometimes used when we get IP fragments, IP packets which are fragmented. This hardly ever happens where we get very large IP packets such as 64K. These obviously don't fit into Ethernet data frames, so what we can get sometimes is fragmentation of IP, where it will be fragmented at the IP layer. So then the remote system builds up these fragments. What's more common now is that the data packets are created with a knowledge that there will be a certain frame size required for Ethernet, so there will only be about 1500 bytes in length. The other place is the identification. The key objective of the identification field is to make sure that within a certain time window that all the IP packets are unique, so that it doesn't get them mixed up. Within TCP we can have a covert channel could be placed in the urgent pointer or in the data offset field. So let's look at an example of how the identification field might vary. So this shows a Linux system. We can see here that we just look at the next one. Sorry, this is the Windows. The Windows, an example of the usage of the identification field within Windows, and we can see what we have is that we'll start off with some random identification number, and then each data packet has this value incremented by 1. So if you look at the equivalent Linux version, we take a certain value, increment it, and then every so often it will then change it so that it takes a jump. So the Linux version goes a little bit like this. Where the Windows version, the identification field will be linear. So let's see if we can have a look at our toolkit again. To see if we can find an example. There we go. So we take the Windows captcha. Okay, so this is an example here, and what we'll do is we'll view it in text. So if we look, there is the identification here: 140, 142, 143, 147, 149, 150, and so on. So it's a linear increase in the identification field. If we now look at our Ubuntu version, this takes a little minute to load up. We should find that it's linear and then it will take a jump. So many different systems implement the TCP IP stack in different ways, and we can see that Windows and Linux obviously vary. So the identification field, there we go, there's an increment and so on, and if we keep going down we can see here it's taken a jump. Now it's down at 80. Okay, so there is a vagueness with inside the TCP IP stack, and it's possible to fingerprint the operating system from this. For data hiding, we find that certain files have standard signatures that it's possible to search for. So if data has been hidden on a file system, it is possible to do a deep scan to actually determine hidden content. So the way most file systems work is that we have a file allocation table, and this is so important that we typically have two versions. If both versions are corrupt, then the disk is almost inoperable. And what we get is, at the start of the disk, this file allocation table defines all the names of the files on the disk and then provides a pointer to the start of the file actually on the disk. So if we said that this was the start here, then we get our file content, and then at the end we then get a link to the next position on the disk, and we might get the next part of it, and then so on until we get to the end of the file. So it's this chained approach that we end up with files which are clustered on the disk. So what we can do is that if a file has been deleted, what can happen is that just the first character of the actual file name is erased, but the pointer to where the file is on disk is still there. Also, it might be possible that sometime in the future that part of the file has been erased or overwritten by another file, but fragments of it still exist on a disk. So with disk forensics we can actually go and read parts of the disks even though the actual original file content has been mostly erased. Okay, so one way that something could be hidden also is that the name of the file could have been changed, in this case from a GIF to a DLL, So when a search is made of GIF files, then they might not come up. Each file though typically has a standard file signature. So in this case, GIF, the first few characters, the first few bytes on a disk for a GIF file are fairly standard, and we have GIF 89AD or 47, 49, 46, 38 and so on. Some other standard file signatures that we can see for graphics files. For JPEG we see GIF, PDF we see %PDF at the start and EOF at the end. For zip files we see the standard signature of 50, 4B03 or PK. So let's have a look into our toolkit again. So the toolkit is stored in this part is stored in the binary reader. So what we'll do is we'll just view a GIF file. See, here is the standard signature for a GIF. If we can find a JPEG, we can see the standard format that we get for a byte stream is this, and we also look for the GIF header for the information. We can also see other things within the JPEG file. There are usually some metadata, such as the creating package, and for photographs we can get extra information such as where it was actually taken. So let's have a look at our zip file. So we have a standard header here, and there is our standard version of the zip file. We can see here that the header also contains the information about the files inside the zip file, and we can look down there like that. Okay, so if we take our first mystery file, this looks like a GIF file, and hopefully our system will identify it. Second one again looks like a GIF file. Third one, that's actually a WMF file. Some other standard signatures, we can identify Word documents. So PowerPoint is identified with these standard signatures. Obviously these signatures could occur in other places in a file format, in a file system, so we can never be sure that it is actually a PowerPoint file, but it usually gives us a range of options for that. Doc file, Microsoft database. We look for this file, or we can look for StoreJetDB. Let's see if we can actually find a Microsoft database file. Maybe not. So we have Windows Outlook, post office files, spreadsheets, and the thing to notice here is that the new formats for the XML content for Microsoft Office actually has the PK at the start, which identifies that it is using PK-zip compression methods. So 504B is the same as the header that we have here. So below here we have an example of a Microsoft database. So there's the standard JET signature and the standard identification of it. This is a docx, and we can see here there is the standard start of a JPEG, of a PK-zip file. A few other ones, flash files. We look for this signature, MP3s, TIFF files, and so on. So we can find WAV files, RAR files, and movie files, and so on, looking for a standard file signature. So we can see in this case we have a flash file, and let's see if we can find the standard file signature from there. Let's see if we can find a flash file. And here we go. So this is the contents of our flash file, and at the start we can see the standard signature for a flash file there. Okay, so that's given us an overview of some of the methods that a malicious person might use to hide or obfuscate data. So we looked at some of the main obfuscation methods, such as encryption and hashing, along with encoding. We had a look at some of the ways that data was encoded to possibly hide its original content, give a better understanding of encryption and then some of the methods that might be used to uncover malicious content, and then how our file systems can be discovered.